Hello, I'm Sean McCord. I'm the CEO of Psycore Systems. We do this kind of stuff: Asterisk, Kubernetes, embedded systems, automation, various things, and we like to make monitors shut off too. So the talk today is going to be, as James just said, about running Kubernetes and the supporting services in the Kubernetes cluster environment. So before we start, two terms that should be familiar with you, but just to put them in a context that we'll be using them. Container is basically an application which is running inside a namespaced environment, that being a cordoned off area of a larger system, usually from a static and redistributable image. So ideally, we have something that looks roughly like this, that we can plop around on trucks or move around on wires, however we want to use it. So essentially, and primarily what we want them for, is that containers are self-contained, static, can be signed, and have unique identifiers, hashes that can be verified. They're simple to interface with and universally applicable. And we want to try and abstract and isolate them as much as possible, so that we end up with fast and lightweight applications that can be deployed in any number of ways. Kubernetes is a cluster operating system. So if you think of the operating system that runs on your computer, a cluster operating system is an operating system that runs on a number of computers in a cluster. It's built to orchestrate a large number of container-based applications across the cluster, across the multiple machines. So we take a single container and we add Kubernetes so that we can manage any number of containers within the cluster. So Kubernetes overall ties the containers together. It provides names by which they can be accessed, DNS environment variables and such. It maintains the states of all of the containers in the systems. It handles automatically schedules, rescheduling, starting, migrations, any number of things that you would normally have to do manually, even literally manually. It abstracts configuration away so that you can use the same image in any number of use cases where the runtime environments differ. It scales and load balances automatically, so you can set parameters by which applications independently scale from each other while still maintaining uniform namespaces by which they can be called. And it manages storage. So once you put something in a container, you want to separate out, of course, all the variable data, so you need a way to manage what does have state and what does have store. And so Kubernetes supplies facilities for managing storage. So all of that, we don't really care about high-level nomenclature, but what we really want to know is how do you get Asterisk and voice systems on Kubernetes? And we're going to be talking about 5 hurdles to this process to begin with. There are probably more, but these cover the basics. Containerization, how you make a container, how you make a container image, how you manage to deploy it. Configuration, how you split that massive set of configuration files, for instance, in Asterisk, into something separable and redistributable and sufficiently dynamic for various runtime and highly dynamic environments like Kubernetes. How do you do networking? How do you get the NAT working? How do you get the signaling, the SIP, and the RTP to pass through the system? Scaling. How do you separate the deployment of your application such that you can independently scale the pieces and leverage Kubernetes to do so? And finally, Kubernetes is a completely dynamic system. You have things coming in and out, containers going up and down all the time. You have to be able to move immediately to any changes and migrate and update your systems. So, containerization first. So this basically is covering building the image itself, guidelines for that building, and this concept of the entry point script. So there are several ways, of course, to build your containers, but fundamentally, what you do is, like any configuration manager or any recipe that you build, you set a set of steps, codify them into a file, and a Docker file in this case, and then run an interpreter, Docker for instance, to build the image from these steps. So it's important that you work from a set script, a Docker file to build these images so that they are reproducible. You don't ever want to use the golden image type of mentality where you take an image, go in and edit that image and save it as a new image, because it's incredibly difficult to then recreate it if you ever need to change anything about the initial. So Docker provides facility for that with the Docker file, and there are any number of ways to do that. Don't worry about the specific details of these. All of the files, by the way, for this talk and for the demo are available on GitHub, which I'll give you the link to afterward. General guidelines, when you're building your containers, the container should have no variable data in it. Every time you run a container, it's running in a layered system, a layered copy-on-write system, whereby every change adds a new layer to the file system. So the more changes you add to the file system or to any of your data stores inside the container itself, the slower that system is going to be, the more complicated and the less efficient it'll be. So general rule, keep variable data outside of the containers themselves. Don't store configuration data in the containers. The idea is to make a single container that is flexibly applicable to any number of situations. So the more configuration data you have inside, the less flexible that container is. You don't want to contain secret data. So passwords, keys, any kind of thing that shouldn't be redistributed. Although you can run private repositories, and it's often a good idea to do so, it's just as bad as putting passwords and stores inside a Git repository. It's far too easy for you to lose control of the images and have them exposed. And finally, just for size sake and for the sake of not running multiple things in a container, try to keep extraneous software out of your container. So entry point scripts are important aspects to building your container. These are scripts or binaries which are run before the primary system or run to the primary system, which allow you to do various initialization and configuration tasks. So for instance, here we have, we're making sure that Asterisk has voicemail directory, spool directory. Because that's variable data, we don't want to bundle it into the container, so it'll frequently be a volume or a volume attached to a var, so a prefix directory. So we go ahead and make sure that directory exists, however it may be. We check and make sure database connections are live before we actually execute things. We check and make sure that we have a configuration if we have configuration being generated from outside. So that's what we're doing here, is checking to see that we have a manager, an AMI configuration before we start. So generally, it's a way of supplying standardized checks before you run the container itself. And finally, at the end, we run Asterisk here, and that being the container itself. Configuration. So how do you get that configuration out? Well, there are, of course, a number of ways. Databases are very typical. So whether you use Asterisk runtime or whether you use glue scripts to pull data from databases, they're always an easy way to abstract that variable data from your container. But in Kubernetes, we also have concepts like secrets and config maps and configuration volumes, which we can use to great effect to separate configurations. So secrets and config maps are essentially key value stores that are built into Kubernetes that allow you to store either variable or semi-structured data which can be referenced easily from the containers. They can be exposed as either a directory of files, so the key is then the file name, and the contents of the file are the value of the key. So if we were to mount this secret here of mail, it would have 3 files in the directory containing the values of those username, password, and host. You can also expose them as environment variables, by which each of these would be showing up as an environment variable. You would have an environment variable username inside the container, and the value of that environment variable would be the value of the secret in here. The only real difference between a config map and a secret is how Kubernetes handles it. So while this looks like gibberish here on the username and password, it's really just base64 encoded. It's not encrypted. Don't treat it as if it were encrypted. It's merely to make sure that if you were to look at it in glancing, you don't accidentally just see the passwords. It is easily decodable, so do not treat it as cryptography. But secrets also supply some additional access controls integrated in Kubernetes. Other than that, you can use them interchangeably. Secrets and config maps available in Kubernetes. One thing to keep in mind about them, after you start a container or a pod in Kubernetes, although you can change the content of a secret in a Kubernetes, after the start, that data is set and static within the container as it's running for the duration of its execution. Configuration volumes are another concept. Essentially, this is a volume like any other that you attach to the container when it's running. Volumes allow you, to go back a bit, volumes allow you to attach places to store variable data that are separate from the lifetime, the life cycle of the container itself. So specialized configurations, variable data that has state that needs to be stored across executions. These are good places to use volumes for, and configuration volumes are simply an arbitrary subset of these used for configuration. Networking, of course. Everyone in the VoIP world knows the fun of networking and SIP and RTP rather. In Kubernetes, you are almost always going to be natted. You can work around it if you really put your mind to it, but just count on at least 1, probably 2 layers of NAT. It's not all that scary, and we do have some tools to make it easier, but yes, it is pretty much anathema to anything voice. Generally speaking, your cloud providers do offer, at least on their layer of a NAT, a one-to-one NAT that has 1 public IP with 1 internal IP, which helps a lot. Azure is a notable counterexample. By default, Azure on the Azure Kubernetes service does not give you public IPs, so you're many-to-one NAT. So if you do have border session controllers or border voice elements that need to talk, you will almost certainly want to run a subset of nodes that do have public IPs assigned so that you can assign those arbitrarily and use them directly. So there are various APIs by which you can discover the IPs, and ultimately just understand that you will be behind NAT unless you go through a great deal of effort, and you just need to be able to handle that. In order to help with the NAT, there are a number of proxy systems available. In Voice, we basically use two types of proxies. We have SIP proxies and we have RTP proxies, which proxy those two things. Ultimately, the proxy is there for a few main purposes. Scaling, to allow you to independently scale the worker nodes, in this case, for instance, the media servers that we have Asterisk, from the proxies that simply pass the data. Each worker node can handle a smaller amount of traffic per CPU than the proxy nodes, so the idea is to separate those out so that you can independently scale them. You also limit the exposure. We don't have to worry so much about the security of Asterisk if nobody can hit the Asterisk directly. We also get separation of services, which helps with that scaling again. Having more pieces that are independent is kind of the mindset of microservices to begin with. Being able to independently scale components and independently monitor and control components is part of that separation of service benefit. And lastly, we can reduce the number of network aberrations. So by this I mean, if you're trying to do non-NAT pieces, at least try and keep those non-NAT pieces or things that are aberrant to the standard Kubernetes model as small as possible. So if we separate those things that need NAT and don't need NAT, then we can independently control a number of aberrations in the system, which will make your life simpler and happier inside Kubernetes. One thing that is common that I have seen lots of people try is to use the service provider's load balancers for voice. Don't do this. It will work perhaps for very simple calls, but the moment you have any kind of forking of a call or try and do anything fancy with RTP, it will break. Just don't do it. Use Kamailio, use OpenSIPs, use some proxy for this purpose. Don't try and use a standard web load balancer. So networking, I wrote just a simple little tool for quick and easy discovery of network properties. Works on multiple cloud installations, all the major ones, Google, Azure, DigitalOcean, AWS, etc. It also works on bare metal clusters, and it will discover private IPs, public IPs, IPv4, IPv6, and the public host name for any host. The CLI version spits it out in JSON, which is parsable by whatever. There's also a Golang library, which the CLI tool uses. It's just a simple curlable binary. Being a Go binary, it's no dependencies, just a single binary to do it over. It's a useful tool anyway. So scaling. So inside Asterisk itself, the more things that you can pull outside of Asterisk, the more you can independently scale those components. Anyone using AGI, for instance, has to use AGI on the machine because it's direct execution. Asterisk offers fast AGI, almost exactly the same interface, but allows network abstraction. ARI proxy, AMI, we all offer ways of getting off of the Asterisk machine itself so that we can independently scale. So the ARI proxy, so there are a couple in standard use, the Invisible Ink one and our ARI proxy are fundamentally the same concept. The idea is to be able to abstract Asterisk nodes and instances so that you can just deal with a call, and who cares where it is. Let the system figure out what machine it's on and how it moves through the system. All you care about is a call. It doesn't matter how many instances of Asterisk, it doesn't matter how many instances of Kamailio, it doesn't have however many instances of the app, it just works going through the proxy. So you've heard the term proxy so many times. This is part of Kubernetes. You are almost always proxying and load balancing between any number of services because it allows you an indirection to be able to control the dynamism of the environment. So our own have a few features that the invisible link one doesn't, and vice versa. But anyway, there are two main options out there for the ARI proxy. AMI itself is already network oriented, so it's a single socket by which the communication is made. It, however, doesn't really offer any kind of node abstraction. So you can connect to it outside. And unfortunately, the Astman proxy that does exist doesn't really solve this node abstraction problem. It's really just a way to funnel in additional listeners to a single request or to a single service. So more work is needed for AMI abstraction if it's around. AGI, on the other hand, is a pretty easy transition to Kubernetes. If you use fast AGI, you can use any arbitrary TCP port and socket, and that includes the standard load balancer within Kubernetes. So all you have to do is define a service for your app, the port on which AGI is running, and then tell Asterisk to look at that service in Kubernetes, and you're done. So AGI is one of the easiest things to adapt to Kubernetes to abstract from the Asterisk instance. Finally, dynamism. As I said, Kubernetes is a constantly changing environment. You have different IPs, you have different numbers of nodes, you have different numbers of pods, different services, different routes for anything. You have to be able to maintain a current state of the system that you need to be talking to be able to function each of the pieces, even between your proxies and their users. So a couple that we provide that are useful, again, open source tools. Asterisk Config, which is a simple container that runs as a sidecar container within the pod that Asterisk runs, and separately monitors the Kubernetes API to reactively get any changes to any of the monitored services, pods, endpoints. I think there are some others, network variables. Anyway, any number of pieces of information that may change, takes those changes, immediately rebuilds the Asterisk config, any of the files within the Asterisk configuration system, and tells Asterisk to reload them. So this running as a sidecar allows you to instantly respond to any changes. I'd use the term instantly loosely, but it is less than a millisecond. Respond to any changes in the highly dynamic Kubernetes environment. So if you lose a Kamailio node and a new one comes up, you're notified, Asterisk automatically gets the updated endpoints for its PJ-SIP, and it's reloaded, and you're done. You don't have to know about it. You don't have to do anything about it. It doesn't interrupt any calls if they're up, as long as they didn't go through the Kamailio box that went down anyway, and so forth. Similarly for Kamailio, we have a dispatchers tool which will maintain the set of dispatchers which in Kamailio terms are the list of endpoints by which certain things are namespaced so that you can get them. In common use, we use them to house collections of Asterisk boxes. So in this case, we maintain the set of available Asterisk boxes in the Kubernetes configuration and tell Kubernetes to tell Kamailio to reload every time Kubernetes notifies us that one of the Asterisk endpoints has changed. So all of that detail, we get to see now how it comes together and deploys to a real live system. So we have here a very simple Kubernetes environment. On the left here you see one application running, one Asterisk instance running. We have an audio socket voice interface running, which I'll describe later if we have time. Two Kamailio instances for proxying, and one NATS instance for ARI messaging. You look in the bottom left, you'll see that corresponding to our one Asterisk instance, we have a dispatcher set containing one endpoint of the Asterisk. So, on the right, we are going to call in, and if the demo actually works, scale Asterisk to 3 instances. All right, so we have 2 more Asterisk instances started up. The dispatcher set has been updated, and if we make another call back in, we'll go to any of the others.
Hello, how may I help you?
Scale the Asterisk instances to 8. All right, so now we're scaling up. We have 8 Asterisk instances. Dispatcher set's been updated, Kamailio updated correspondingly. Looks like we've got one of the Asterisk boxes failing to come up on our 3 nodes. We're probably just running them a little hot, but no big deal. Since I don't want to run up my bill too much, I will scale Asterisk to 1 instance, please. And shutting down all the Asterisks but 1. All right, so all of this code is up on GitHub. Every piece of this, including the voice interactions and the tooling, is all on this page. If you can read that URL, that's everything here. So I guess we'll stop that. If anyone has any questions or would like to go through any of these pieces, I will open it up to the floor.
Right,
Alex.
here we go. This is going to be good.
This is perhaps just a general Kubernetes question, but I assume that with the combination of configuration management and template substitution replacement that it offers, there is a corresponding bundle of inbuilt proxies that perform load balancing in a protocol-aware way for various common on-the-wire protocols like HTTP or just simple TCP sessions and maybe a few others. Is it easy to write one's own if one has a kind of bespoke on-the-wire protocol?
So the default load balancer, the internal kind of service load balancer in Kubernetes is not pluggable, and it's just using the kernel to redirect requests. So it's actually an IP tables rule to bounce through. So on the host, it's a very simple system.
New connections.
Yes.
Proportioned that way.
Yep. Yep.
What if they're UDP?
Same thing. If they're UDP, it's just fine. It's the same system. Again, it doesn't matter. It's whether it's UDP or TCP. It will just bounce it. Yes. The question really is, well, what if it's UDP and you need to hit the same box? Yeah. Don't use the internal load balancer for that. Yeah. If it's UDP, use the proxy. Use a non-brain dead proxy.
You surmised the tacit intent of my question.
Yes. Right.
Any more? No, it looks like you get off scot, well, reasonably undamaged there.
So I said if I had time, and if no one else is interested, you can leave. It doesn't really matter. But since it's brand new, I'm kind of
yes,
I kind of
danger.
like it. So the audio socket idea is the intention, very new, 2 months. Anyway, the intention was to get as simple as possible an interface to get audio into and out of Asterisk. So what we probably weren't able to hear, but maybe see, the voice interaction in that phone call was done using the Google Cloud Platform's speech tools and text-to-speech system. That was pulled out of Asterisk using this audio socket mechanism. So what the audio socket is we run the audio socket, and it'll be easier if I just show you the code. So if we look at the Asterisk Config, the extensions, the inbound extension. So what happens when the call comes in? We immediately go to this audio socket. In this case, we don't really care about the call ID, so I just made up a random UUID to give it statically for every call. But the audio socket works with, you give it a call ID, which has to be in UUID format, so just a regular call ID is not sufficient from Asterisk. That's maybe a bit of a stumbling block, but I really wanted something uniform. And then the host and port of the audio socket server. The audio socket server is nothing fancy. It is really just a TCP server that takes very thinly structured data in and sends very thinly structured data out. Basically, it is a 3-byte header with a variable payload. The first byte in the header is the type. It says whether it's an ID, a UUID that'll be in the payload, or right now we really only have one other header, signed linear audio. And so then we get the 2-byte payload length and the actual raw data. So it's a dirt simple protocol to implement. And we have a Golang library, of course, because I'm a Go fiend, that implements the audio socket library both on the client side and the server side. But the idea and the Asterisk side implementation is, of course, not language specific. If you can implement this really simple TCP protocol, you can connect to any of the pieces. So because it's TCP, it's connection oriented and bypasses Alex's problem of the multiple connections going to the same place. So we can use the regular built-in Kubernetes service load balancer to handle it. And it just passes the audio back and forth, and we connect up on our service side, which is here. In the voice side service. And this is our audio socket service implementation. I wanted to go to GoDoc. No, I didn't mean it. GoDoc.org, github.com, systems, Asterisk 8S demo. If you don't know about this feature of Go, it's stupendously useful. Automatic documentation for any particular project.
Does it write itself?
Yes, it writes itself. As long as you write in the appropriate comments, anyway. But I can't seem to remember my own URL, so. Asterisk K8S demo. And live demo, and this is why I should have built a link for this before, but oh well. Voice, and it was service, right? There we go. Okay. So, All right, yes, because it's not actually a package, there's no usable documentation from it. So ignore my dangerous demo that has now dangerously bombed. Let's get back to the repository. And look at this file, ugly as it is in the GitHub viewer. And see fundamentally what we are doing, hopefully, if it is at all. I really wish the viewer had folding. Oh well. So our main call handler, we take in, synthesize the speech, sending it to Asterisk when we get it. So this send audio takes the audio content, which is conveniently in signed linear format, spits it out through the audio socket, which then goes to the Asterisk channel. Then we loop through waiting for commands, voice commands, to come in. So looking at the process command. Too much stuff. So pipe from Asterisk. This is the receiving side of the audio socket. So we switch based on the kind of packet it is, if it's signed linear, if it's an error packet, if it's a hang up signal, or if we lost the connection. We pipe that out. And this is the, of course, the receiving side. So we're sending it to Google here with the audio content just as a payload. Again, matches up really well because Google expects streaming signed linear audio, and we get signed linear audio out from Asterisk via the audio socket. So it's really just connecting the pipes together, and so that's what we have. So being a TCP service, we can service any number of connections on it, of course up to the port exhaustion threshold of 65,000 anyway. It maintains state, maintains connections. We don't have to worry about the packets being lost or maneuvered. And that's pretty much it.
Brilliant. That was an extremely comprehensive little tour. So any more questions now? Because we've still got a couple of minutes. Anyone? No? Well, thank you, Sean, for that. I've actually learned quite a lot from that. And you've definitely got the basis of a Swan Prize dangerous demo in there. And so you're not going to escape. You're going to be doing that again, but with extra danger tomorrow, I think.
Extra danger?
Yeah,
this
well,
was
we'll talk about
danger
that.
enough. Have you noticed there is no internet quality here and today? It was fine yesterday. Today, it's just absolutely abysmal.
Yeah, if I had $1 for every time I've heard that particular line, but...
Yeah, well, it's just incredibly difficult to do any kind of programming remotely on my workstation when if I type 2 characters, it takes 30 seconds for it to actually show up.
But I was very impressed. Your demo worked. You spoke to it, and it spawned up lots of instances of Asterisk, which is, in itself, is pretty
But
pretty
more
marvelous.
importantly, spawn them back down.
Yes. Yeah, and I loved sitting here watching the smile on Matt Jordan's face when you did that. The sheer delight on his face. It was a picture. It's very, very cool. So you're definitely going to have to do that again, but with more danger tomorrow.
More danger. All right.
Yeah.
More danger.
Okay. Well, if there are no more questions, let's say thank you to Sean in the usual way.